So today we're going to be talking about the various types of solids, and this is in continuation of the previous lesson on the types of bonds that included covalent, ionic, and metallic. Those are the three types of bonds that we will be coming back to visit due to the fact that they are the foundation of all the matters that exist that are not just pure elements. Even some of the pure elements, when they're in solid states, will have some kind of bonding happening as well. But overall, what we're going to be doing today is focusing on the types of solids, because those are what we will observe at the macro scale. That includes multiple atoms and combined in a certain arrangement that is repeated, and that is what we're going to be addressing today. So this is the part 2 of the types of connections and as well as the types of substance that we can observe. So in this first model, you will see that there are 4 types of solids in model 1, starting with the ionic solids on top. These ionic solids are usually made up of ionic compounds, which usually are some kind of positively charged cations, as well as some kind of negatively charged anions that are also located next to the name. So iron sulfide, for example, you have iron, which is a positively charged metal ion, as well as sulfide, which is a negatively charged ion. So in this case, the two of them combined together makes this iron sulfide. Same with calcium bromide. Calcium is going to be the positively charged, while the negatively charged is going to be the bromine, or in this case, bromide. And we'll get into naming in the next few classes regarding ionic compounds as well as covalent compounds as well. So calcium bromide is just calcium and bromine combined together. Sodium chloride is going to be that similar idea here. In this case, sodium chloride, sodium is the positive ion. That is going to be slightly positive. And then the chloride ion is going to be the slightly negative one, because remember, chlorine are very electronegative. Same with bromine, sulfur, they are more electronegative than their metal counterparts. And as a result, they will hold on to the electrons and thus forming this ionic solids. Molecular solids, on the other hand, are defined by this characteristic, or the name specifically suggests they are made up of molecules. What defines as molecules is any two atoms joined together. And in this case, you can see that they are small little molecular units that are joined together. And because these molecular units are joined together, they are what we call the molecular solids. These are typically made up of nonmetals, and they are typically covalently bonded. And these are one of the types of solids that have covalent bonds in them. Next up is the network covalent solids. Network covalent solids are, again, the word network is going to be a key part here, as well as covalent. So the primary bond that's between them is going to be covalent bonds. But what is different about this one is these are not made up of molecules. So the different contrasting point is that molecular solids are typically made up of molecules, whereas network covalent solids are not made up of molecules. And these are considered to be repeating patterns of a certain ratio, which are what we call formula units, which we're going to get into later on. So, for example, silica, or silicon dioxide, that has 2 oxygens and a silicon, just like carbon dioxide is, they form connections between the silicon and the oxygen, as well as between the oxygen and silicon, and vice versa, so creating what is looking like a mesh network. Just like silicon over here, they're also going to do the same thing. So they're just going to be connected together, but they don't form molecules. They're not distinct units by themselves. Last but not least is metallic solids, which are essentially made up of mostly metals, such as platinum. Copper and zinc together was what we call brass. You also have bronze, which is copper and tin, and also various other combination of metals, but essentially mostly metals makes up metallic solids. So the 4 different types are ionic solids, molecular solids, network covalent solids, and metallic solids. And just as a quick review, metallic solids are only made up of metals, and network covalent and covalent molecular are usually of covalent nature in their bonds, and also they're usually non-metals, specifically, or metalloids, usually. And the last but not least, ionic is usually of metal and non-metal. So the two different kinds make up the two different types of ions that mixed together makes the ionic solids. So just as a quick review, ionic is usually metals with nonmetals. Molecular and network covalent solids are usually made up of covalent nonmetals, and metals are usually made up of metallic solids are usually made up of just metals. So in question 2, you will see that there are checks in these boxes, and that's what we just kind of talked about. So again, molecular solids and network covalent solids are the only two that are all nonmetals. Metallic solids, on the other hand, also just have metals, and that's the only type that has just metal, hence the name metallic bonds and / metallic solids. And the next one is ionic solids, which usually have atoms of metals and nonmetals. So they have both types in there due to the fact that you have to have a positive metal and a negative anion that are usually nonmetals. And the combination of the two makes up the ionic solids. Those are the ones that will have formula units as well as the network covalent solids, as in they have repeating patterns of certain number of atoms of each element. So for example, sodium and chlorine together make sodium chloride. It's usually NaCl. So for example, NaCl would be a fixed ratio, or magnesium oxide, that's a 1-to-1 ratio. But you could also have sodium oxide, for example, NaO2O, because sodium will only want to give up 1 electron while oxygen wants to take up 2. And that ratio is going to be fixed throughout the compound, but not acting as a single molecule because they are not separated. Once they separate, they form ions, and that's not what a molecule is. So therefore, it's not considered to be a molecular structure. Molecular structure, on the other hand, is talking about each of these will form a particular unit, such as H2O or CO2. These are specific units that will be able to detach from each other, and we're going to get into why this is important and how is this different from ionic and network covalent solids. So for example, water molecules, even if you heat it up, it's going to only become water vapor. Not going to be, it's going to go from ice to water, liquid water to gas or steam water. It's only until you reach an extreme temperature that the hydrogen and oxygen will separate. But essentially, during this time, they function together as a unit. That's what we call having a molecular structure. And that is true, too, for CO2 as well. And the primary attractive forces between them, ionic solids will only have ionic bond. And this is where we introduce a new concept called intermolecular force. The key word here is inter, because when you look at the word inter, you should think about internet. Internet means between networks. All right. Interscholastic means between schools. So essentially, inter means between things. So intermolecular means between molecules. And that is going to be a key word that will come back later when we talk about the various solids. And obviously, between the covalent network is going to be covalent bonds. And last but not least, metallic bond is going to be between the metallic solids. All right. So in this case, again, molecules are distinct molecules, as in they are functioning units whereas formula units only represents a repeating unit in three-dimensional with no distinct molecules. So essentially, you're either formula units, where there is a repeating ratio that is the same, or they're functioning as individual molecules, and that is the difference between the two. So how we actually determine what type of attractive forces between the various solids is actually based on what happens when those solid substances are heated. When we heat something, we're adding a lot of energy to it. And that what happens after when you add the energy to a certain substance, the weakest attractive force in the solid will be broken and overcome. And when you overcome that basic attractive force that is holding it together, the solid will melt. And because of that, there are different ways that we use melting point as a separation, a way to distinguish between the various types of solids. By having those solids melt at different temperature, you can also get a sense of, is this a stronger attraction or a weaker attraction? And we're going to talk about those in the next part. So when you are melting down ionic solids, for example, you're breaking up that ionic bond. When you're breaking up a molecular solid, you're breaking up those intermolecular forces. And when you're breaking up the network covalent solids, those covalent bonds will be what is broken. And last but not least, metallic bonds will be what's broken in metallic solids. When you are breaking them down, what happens is ionic solids are going to turn into ions, both positive and negative ones. Molecules are going to be functioning small units that are neutral. Atoms and particles is what happens when you break up network covalent solids. So they are also going to be smaller atoms. In metallic solids is going to also be metallic atoms that break up afterwards. So the key distinction here is that ionic solids is the only one that separates into ions. The rest of them are going to separate into non-charged particles, such as molecules or atoms. Network covalent ones are usually nonmetals or metalloid atoms, but essentially they are not going to be charged. So let's take a look at the matching parts. So the metallic solids are usually going to be made up of metallic atoms that have very loose electrons that are held together by a sea of electrons or metallic bonds. So that should be pretty straightforward. Molecular solids are usually non-metal atoms, form molecules. That's the key word here. Molecules is what defines a molecular solid. And they are connected together by covalent bonds, but that's within the molecule. The molecules are held together by intermolecular forces of attraction. So covalent bond is present in, for example, water connected to another water. The bond in here is intermolecular forces, which is not really a bond because we talked about the three types were covalent, metallic, and ionic, and intermolecular force is not one of them. But the bond between the H2Os, those are covalent bonds. So those are within the molecules. Those are covalent bonds. Those are much harder to break. Intermolecular force, on the other hand, is much more easily broken. So that is going to be a distinction that we're going to come back and talk about more in the next few lessons. Ionic bonds, on the other hand, are pretty straightforward. They are just metal and non-metal atoms. They usually form the positive, and this one forms a negative ion that have alternating positive and negative ions held together by ionic bonds. All right. And last but not least, network covalent bonds are nonmetals, usually, or metalloids, that form as a lattice structure that usually have some kind of formula units, and that is bonded together by covalent bonds, so hence the name network covalent. So one of the questions that you will see that I need you to answer is, if a particular solid has a very strong attractive force, would you expect the melting point of the solid to be relatively high or relatively low? Explain your reasoning. So if you have a very strong attractive force, what should you expect? Well, I would expect it to be a much higher, relatively higher melting point. Why is that? Well, if it's a strong attractive force, to break that bond or to break that attractive force, to weaken it to the point that they separate, requires more energy. So I would say that would require a relatively higher melting point to achieve. And that's one of the questions that I will be checking. All right. So let's get into Model 2 and see how that factors into real-life compounds. So for example, which type of solids usually have the lowest melting point? So let's take a look at all the various types. So where I'm going to circle the ionic ones in black. Those are the melting points for ionic, melting points for molecular, melting points for network covalent in red, and then green is metallic. So if you zoom in and look at it, which one have the lowest numbers? I would argue that molecular, in fact, has the lowest. They have 2 negative numbers and water at 0 degrees Celsius. So it is molecular solids because, is that consistent with this? Yes, because intermolecular force is not an actual bond. It is considered just to be an attractive force, which is the weakest one. And same can be said about enthalpy of fusion. Well, what the hell does that word mean? Well, that is enthalpy, meaning it is the amount of energy that is needed to melt 1 mole of that substance. So it's the amount of energy you need to melt 1 mole of that substance. And the one that has the lowest number, again, the honor goes to molecular solids. That has mostly single digits. The rest of them are all double digits. And that is going to be, again, the lowest one. Which makes sense because, again, the enthalpy of fusion is going to be lowest for molecular solids because they are the weakest form of attraction. In the order that goes from molecular to ionic to metallic to network covalent being the strongest and the highest. All right? So, there is a lot of overlap in properties among the 4 types of solids. For example, platinum have higher melting point than several network covalent solids, but most metallic solids have a much lower melting point. So these are not as clear-cut as we would like it to be. So just keep in mind that these are not as clear-cut as they could be. They are just more or less a guiding suggestion. Most of them should behave in a certain way. And we use these numbers as a ballpark way of saying, hey, I think this is one of the reasons why I believe this would be an ionic solid, because it has a relatively low melting point compared to the rest. So what could be high, what could be low, that's going to be the range that you will need to see the data in. So obviously the lowest one is going to be molecular, then followed by ionic is going to be the second lowest, followed by metallic ones, which is in the 1,000 to mid-1000s. And also, like we talked about how platinum and nickel are kind of exceptions. Like diamond, carbon, it's just really, really high. That's 3,000 degrees Celsius before it melts. So all those are just suggesting that there is a relative relationship between the types of solids as well as the type of intermolecular attractive force that's holding them together. So let's use that concept to try to apply to this case here. So this is one of the questions that you will need to answer as well. So if you have chlorine, which has a very low melting point and has a relatively low enthalpy of fusion, and it's also made up of nonmetals and nonmetals, what type of solid could it be? So it should be probably thought of as molecular solids because of the fact that it is very low in terms of their enthalpy of fusion as well as the melting point. So it's probably a molecular solid. Same with this one here. Those numbers are both fairly low, negative 87 and 2.41. Those are pretty low numbers. This is probably also likely to be molecular. Titanium, on the other hand, is 1668 and 20.9. Well, what is titanium? hopefully you know that it is a metal. So if it is a metal, what kind of solid could it be? Sodium bromide, slightly lower melting point, but a slightly higher enthalpy of fusion. What could that be? So I'm going to be checking number 11 for you folks as well. And then last two examples, boron, which has a very high melting point at 2076 and then 50.2 kilojoules per mole of enthalpy of fusion. What type could that be? And mercury, which is a metal, has a negative 38.3 melting point, this is a major exception here. There's another one that is gallium that melts at 27 degrees Celsius and also very low enthalpy of fusion. But what could that be? And so if you can justify your answers, that is going to be the important part. All right. So there are a lot of properties that can be, other than melting point, that can be used to categorize substances. Right? So you can also use conductivity as well as the term solubility. Conductivity measures how well do they conduct electricity. Can they send electrical impulses through easily or not so easily? Another part is, can they dissolve in water? If they can dissolve in water, they are considered to be more or less separated. So for example, if you have substance that dissolve in water, if you can separate out, they tend to form ions, and there is a high probability of them conducting as a solution. So you can see here, the ones that are conductive as liquids are usually the ionic substances. And another type that is usually conductive in both solid and in liquid phases are the metals. All right. So that is going to be the important distinction here. So the reason why ionic ones conduct electricity and when they're dissolved into liquids or when they're dissolved into water is because they form ions. Ions carry a charge, and those charges can move the electrons back and forth. Same with metals. Metals will have a loose sea of electrons that allow for the electrons to move freely from one place to another. All right. So, which type of solids is usually soluble in water? Well, that is going to be the ionic solids. Metallic solids are going to be least soluble due to the fact that most of them don't do that, as well as network covalent solids too. So those are both correct answers for that one. So network covalent solids are usually not dissolvable. Because you can see here, network covalent solids are not usually dissolvable. Well, technically, carbon dioxide can, and it actually ionizes the water, but that's a little bit different. So those are the two for 12B. You have metallic solids as well as network covalent solids that do not dissolve in water. So which one is the most conductive in solid state? That is going to be only the metal ones that do, because metals have free electrons that can freely move about. Whereas ionic ones, once they are melted, it will form free ions, and that is where they can also conduct electricity throughout. All right. So why these conductivity wouldn't exist for some of these data charts, if you look up here. So for example, iron sulfide, if it doesn't dissolve, then therefore it cannot be tested to see whether or not it is conductive as an aqueous solution. So the reason why is they could not be dissolved. All right. So when we are examining all these, remember that this is only part of the picture. This is not the whole end-all be-all way of determining substances, but this is another helpful data point that you need to take a look at to figure out if something is a certain way or it could be configured in a certain way. So solubility is one of them. Conductivity is another. And that's where you have to be aware of that we are talking about multiple traits that you need to pay attention to, such as melting point of fusion and also enthalpy of fusion, both. So there is always more than one way that you should check out a substance to make sure it is the type that it should be. So engineers use different materials to perform different functions based on the properties. So for centuries, we have used metals for tools, more recently, electrical circuits. What properties of metallic solids make it well suited for this purpose? Well, it has free flowing sea of electrons that allows for conductivity. And that is one of the reasons why conduction, if you will. It allows for electrons to freely move around and move from one location to another. All right. So in the next class, we will be classifying various compounds based on the properties of whether or not it is soluble, whether or not it's conductive as a solid, liquid, or in an aqueous state, and also its melting point, enthalpy of fusion, and what their electronegativity values are, because those are all factors that we will be using to figure out conclusively what type of solids and what type of bonds are holding those solids together. Hope this video was helpful in completing this activity. Have a great day.